Thank you very much, Wes. Good to be with you again. And if you're looking online, it's amazing how knackered you are at the end of day one of a show like this. But it's crazy. So a little bit of background on me. If you weren't here at the previous presentation, I was spent 22 years working for Telco Land, and then migrated to Venderland in 2010 and joined Appear 6 months ago to the week actually. And just like to plug my Appear podcast, Time for Tea with Andy Rayner. Do subscribe if you get a chance. We do a podcast every month on a technology or a related media commercial topic. So this afternoon, I want to just remind us of one or two of the trends of the industry. As a media industry, and I said this as part of the presentation earlier as well, we're moving from the bespoke to the generic. So everything from the connectorization, where we used to have dedicated broadcast connectors, BNCs for video and XLRs for audio. Nowadays, and more progressively as we move forwards, everything is native Ethernet connected. So we don't have bespoke physical interfaces for media anymore. We're also moving from private leased lines to internet connectivity for lots of production cases, and that was the presentation I did earlier. So if you're interested in that, do go check it out. Similarly for RF, but the area that I wanted to talk to you about this afternoon mostly is media processing moving to virtualization. So taking those media functions from dedicated physical appliances and moving them into compute functions that can be hosted on servers. Those servers can be either in your infrastructure, in your facility, or, to quote Felix Perron of CBC, actually dematerialized into a server that's actually hosted in somebody else's property, somewhere else on your behalf. Now, one interesting term I think it's just worth talking about for a few seconds here is what we mean by cloud. There's a lot of talk about cloud, and basically some people equate that with public cloud, as in something that's provided by GCP or AWS or Azure, etc. I think in the terms of the technology, talking about cloud in the instance we're talking about here, very much referring to anything that's being put onto generic compute. That could be hosted in public internet, and there's some very interesting, there's another good presentation I can recommend from earlier today from Imagine, from John Mayotte and a colleague, talking about the maths of the efficiency of the cost efficiency of hosting on private compute versus public compute. So do check that out. But for the purposes of this conversation, I'm talking about moving to compute regardless of where that's hosted. Another observation which actually plays into this, again, this is a slide I've used several times previously. This is actually from the DPP work, which we did 4 years ago now, is that the traditional on location, everything on the same location production that I've got at the top there is now no longer the norm. More and more of the acquisition, processing and storage and control layers are geographically dispersed, and that's for reasons of efficiency in terms of use of equipment, in terms of use of people, and for environmental reasons. So all of those good things. Now, in the heritage of video for the last 90 plus years, we have had what I would call a linear data flow. What we are moving towards as we move into compute to actually virtualize the infrastructure, we're actually moving from these linear elements that you can see on the edge here, where effectively all of the information is conveyed in a linear manner, equivalent to the raster scan, which originally was the way the video was actually sampled and replayed to you on a CRT. More and more, as we move into this non-linear, time-aware software processing chain, that data does not need to be handled in a linear manner. And most importantly, computers don't work in a linear manner. So when we did 2110, the standard, and we started looking at synthetic sources, we actually came up with some profiles for that, but we were still very strict on making sure that compute was actually presenting 2110 data in a linear manner. There's a whole part of the recommendation -21 which actually defines the linearization process and the limitations of the linearity that you're allowed to have to make it work. Now there's a good reason for that. The reason for that is 2110 is based on UDP. If you don't have hygiene in the linearity of the flows, once you start aggregating traffic, you lose data because you actually have overlapping constraints, buffers overflow in switch fabrics, and then you actually lose your data. And because you're carrying at UDP, you actually lose that for good. As we move into this nonlinear compute world, we actually have to lose the UDP element as well, or the UDP natively as it is, because we actually need to actually still have integrity in the data transfer in this world. But obviously, TCP is a protocol, and there are other protocols that various cloud providers, etc., use, which are effectively UDP with ARQ mechanisms that sit underneath them to transport. But fundamentally, you need to guarantee the integrity of the transfer, even if you're time linear. Now, coming back to why are we looking at how we manipulate this data and hand it off within compute in this compute friendly way. You're going to have to excuse me. I've been talking a lot already today, and I've got a can of Diet Coke with me, which I'm going to now drink a little bit of as I do this. So one of the things that broadcasters and content producers in general have been used to in the appliance world is best of breed. So they will choose a multi-viewer from a vendor, they will choose a vision switcher from a vendor, they will choose a replay server from a different one, etc. They will build up the portfolio of the production capability with best of breed, and people have favorites of all of these within the industry that they're working. Now, what we have not yet got to in an interoperable way in compute is actually a way of doing this in a compute native way. So you know, the idea is that the end consumer, the content producer, could actually choose a software component of a multi-viewer, similarly for vision switcher, replay servers, graphics, etc. Now, there are a couple of vendors that are purveying a closed ecosystem that actually allows you to do this to some degree, but that's when these different providers have signed up to a closed ecosystem that's actually managed by a single vendor. What we've been trying to look at within some work that the Video Services Forum is doing is actually create an interface that actually addresses what I call here this non-linear time-aware element, but also allows us to actually have these different functions interoperate in a compute native manner. To that end, and here is the reference, I can encourage you to go and look at this. The VSF has recently, about 4 weeks ago, published the draft of what we call the ground to cloud to cloud to ground API. And mainly this is focused about the cloud to cloud bit. So going from ground to cloud in the way that we've defined it yet, and this is not fixed in stone in time, we're assuming that that interconnect from the ground to the cloud is still a streaming linear format of some kind. So that might be TR07, which is JPEG XS over transport stream. It might be TR08, which is JPEG XS 2110 essence. It might be a standard H.264 transport stream being carried there. But generally, at the moment in the world, that is actually a linear stream. Now, I'd just like to say, if we just look back at this picture here, there is no reason in the future why that non-linear boundary has to be at the edge of the software ecosystem. It could be in the future that actually the non-linear data delivery could actually be literally from the egress of the camera onwards. So it could be that the linear stream transport is even less purveying than it is on this picture. Back to here. What we have done within the GCCG is look at an API that actually allows us to do native compute to compute interfacing. And we have come up with a proposal. It's actually based on some work that AWS, to give credit, did, posted on GitHub. They produced something called CDI, which was launched roughly 3 years ago now. And that is a frame-based, uncompressed transport interface to actually hand off data between compute instances. It is limited because it's integer frame, it is only uncompressed, etc., etc. So there were some limitations of the initial posting and the initial work that AWS did. But what we have done within the GCCG is actually taken some of those principles and expanded that. And it's a living document. We've only published the draft. And actually, as I speak in April 2024, we are actually after comments on this. And my dev team in Appear, I know because I sat with them last week, have actually posted a whole load of comments on this specification, because we've actually now started doing a real world implementation of this, and we've actually come across quite a few things that we need to evolve to make this work in the real world. So it's exciting to get to that real world implementation here. Now, there are other de facto industry initiatives and sort of de facto standards that have actually come into place that are actually within this space already. I'd just like to talk briefly. This is not an exhaustive list. I've just put these up as examples because they are things that are happening around. So SRT top left, that is effectively a streaming interface. It is a linear flow of data, or hopefully a linear flow of data. And what that allows you to do is to actually carry with integrity, because it uses ARQ. It uses a resend mechanism to allow the data to be captured. Then there's the Grass Valley Initiative, which is a closed ecosystem that they purvey, which they have various partners in. And they have basically both, in a similar concept, a streaming interface, such as we are traditionally been thinking about, but also a lower level compute interface, which is proprietary. The challenge is, and I'm going to come to that in a little bit, the challenge is the lower you get down in that compute interface, the more challenging it is to separate responsibility between the different parts of the different components in the system. NDI has become a de facto standard in the industry. Again, it's a single vendor closed system, but actually there's toolkits available that many people are implementing, and there is a massive set of capabilities in the industry now. This has kind of become probably the de facto handoff within compute, but again, it's actually linear. It's a linear streaming format. It is actually TCP based, so by default it doesn't have to be. So it actually has that guaranteed integrity capability that we're looking at. I've already talked a bit about AWS and CDI. Other work in the industry, which I'm not going to go into here, includes some from Matrox with Origin and NVIDIA from Holoscan for Media. Just a shout out to some of those initiatives that are happening within the industry. So, general trends for compute media on interconnect. I just really want to summarize this. So this is what I call the traditional streaming interface. So at the moment we have that as UDP. Most of what we do in the way that we do media over IP in 2110 and in other systems pre things like NDI is UDP with or without ARQ. And I say that's fragile. TCP has limitations, but that's what is effectively used. VBR TCP is what's used by NDI. This compute interface, one of the things we've been really keen to do in the standardization work is abstract ourselves from the integrity layer. So the transport layer could be provided by the compute in different ways, and if you go to AWS they'll have one way of doing that, other providers will have other ways of doing it, and if you're on private compute you'll have even yet different tools, but we're assuming the integrity is designed in, and the API that we're defining for this compute handoff is actually sitting above that. So if you actually think about what that looks like now, we're actually saying we've got an API which abstracts us from the guaranteed integrity time-bound compute handoff. So we've actually got various processing functions that sit on this API. Now, before we got to the place that we're proposing here, basically each of these media processing functions was actually going back to a 2110 type format. So it's actually going back to a linear streaming format with all the prerequisites that incurs about stream linearity. And that burns a lot of compute and a lot of unnecessary latency as well by doing that, because we want to be able to natively hand the media off between there. So there's handing data off locally within the same compute, but there's also handling data off between compute instances. And there is technology called RDMA, which actually allows us to actually do this at very high speed between different compute instances. This is something that we've been doing various bits of prototyping with to look at the scalability. This plays back to the genericity I was talking about at the beginning of the way the industry is moving. We want to leverage generic IT processes wherever we can. We don't want to develop specific broadcast stuff. We want to be able to focus on the broadcast applications, not the underlying transport technology. So RDMA as a toolkit is becoming incredibly useful. The timing is really, really important. So one of the things the last 90 years has done is continually purvey a linear flow of data. What we are doing by going into this compute world is actually saying we don't need to do that anymore. We can handle clumps of data and shove them out when we're ready. Now, they're probably going to be integer frames or integer partial frames of data that we're handling, depending on the latency construct we want to have. But we don't have to put it in a linear format, but there is a prerequisite then. The timing information associated with each of those clumps of media data has to be preserved right from the origination. Because the reason we've got away within 2110, etc., of actually being able to do this is because they seamlessly butt up, and actually you can reconstruct time just by reinserting things together. If we're actually going for bursty compute handoff, then actually that goes out the window, and we need to be able to do that. Latency. So one of the challenges we have as an industry is the way we're actually moving forward is we're actually inducing increasing latency in the workflows. I use the example of an SDI video router, video switch, a video mixer used to typically from the key vendors maybe have a latency of like 3 or 4 lines. With unlimited, with 6, 7, 8 MEs as part of that, DVEs. Now, every 2110, that's linear streaming 2110 device, has a frames delay, because although there are mechanisms within 2110 to define an offset of timing, everyone's scared to do it. So basically what we end up doing is every device wants to go back to the start of frame exactly. So even if it's only got a processing time of 200 microseconds, it costs us 20 milliseconds to put it in the line, which is very, very frustrating. So what we're also doing as we move into compute is we're actually tending to have designs which have frame buffers both at the ingress and egress of each processing function. So again, even if the compute function is only a very small amount of time to actually execute the process that's required, we're tending to just to de-risk things by having many integer frame buffers, and we can easily build up significant additional latencies even on top of those I was talking about with 2110 just by doing that. And the thing is, there is no need to have anywhere near that level of buffering if we develop an ecosystem that can do it. In addition, all the thinking currently in compute is integer frame based. What we did with JPEG 2000 compression between 2010 and 2018 is actually move from saying, rather than send whole frames, we're going to stripe, and we're going to send a fraction of a frame. Maybe it's a fifth of a frame, an eighth of a frame, whatever. There's a pro rata reduction in latency by doing that. So one of my tenets is we need to have the option in this compute interface to actually hand off partial frames, so we can actually, again, reduce the aggregated latency. As we do media functions on compute, redundancy architectures come into play. Again, I think there's two questions here. One of them is what level of redundancy is needed? Obviously, we can do the same as we have done traditionally with appliances and have two systems that are running in parallel. They're parallel fed with a source. They're working, if you like, hot, and actually continually processing. That's an entirely valid approach. And typically, those would then be running on two different compute instances, either privately hosted or two different AZs if you're in AWS land. Now, the other option we have for resilience, most of the way resilience is done in the compute world, is actually you have orchestration-based tools which actually do the redundancy in compute. And it really depends on the resilience and the recovery time you need. If you've actually got a failure scenario where it only happens maybe once every 6 months, you may say 2 minutes to reboot once every 6 months when you have a failure condition is an acceptable time, in which case you don't need to have this level of resilience. You just have an orchestration tool that actually re-establishes the compute at the point you want to go. But that's a choice of the cost of failure of the system of your event. And if it's a Premier League football match, you will probably never do that, because the cost of failure, even if the risk is infinitesimally low, is not worth bearing. It's also worth saying that within compute, we also need to use a lot of input redundancy architectures, because generally the connectivity, certainly within public cloud compute, has nowhere near the level of native integrity that private connectivity has. So we have to actually compensate for that by using either the RTP merge technology, FEC, or as increasingly being used, ARQ technologies such as RIST or SRT. So one thing we can do if we use native compute processes is actually move to what I call containerized media processing. So we actually then can scale up by spinning up as many processes as we need for the input functions, for the media processing functions, and for the output functions. So we actually scale by just building, instantiating more processes. And if we've got the level of interconnect that we need between compute, like with RDMA, then actually that then almost becomes an infinitely scalable capability. Security, isolation, and working together. So one of the challenges, as I alluded to earlier, is the tighter you integrate your compute functions, the more codependencies exist between them, so the more risk you have there. But obviously, the less tightly coupled they are, the more cost there is in terms of getting the data moving between those elements. The control plane is not to be underestimated, and there are some standards. We've been recommending that we actually use some of the NMOS standards to actually do control of these virtual resources, like we do the physical resources. I've got a note here that says ephemeral resources, because one of the challenges we have with the NMOS control ecosystem as it is at the moment, it has no concept of time. It has no concept of forward planning. It only handles the now. And the challenge we have with compute stuff is, if we want it to be efficient, we only want to instantiate it when we need it. So at the point that you're actually doing the design, that media function may not exist yet, because you're only going to build it at the time that you need to have it. And so there is some work we need to do within there's some work we need to do within the control plane to actually look at how we handle ephemeral resources that actually are only going to exist for a moment in time. It's also fair to say that many of these control systems may actually not necessarily natively support NMOS, but it's important that we have vendors provide shims between their own control plane and NMOS so we can do that. With a friend of mine, we've been doing some proof of concept and looking at some of the capabilities that we have, and there's a few conclusions on, as we move things into compute, how things are looking. And I've realized now that actually the text is so small on this slide that I actually can't read it on my preview screen because with or without my glasses, there you go. So, first of all, compute is now very powerful. I mean, that's an obvious thing. Networking with RDMA is also very, very powerful. Storage is significant. Cloud native software architectures are essential to allow us to scale. The interfaces, 100 gig interfaces are now quite ubiquitous, and that means you can actually handle a fair bit of data. I've got some numbers. I'm not going to read all of this slide out, but on a 100 gig interface, this gives you the example of how much uncompressed data you can do. One of the challenges we've made to the GitHub repository from the GCCG is the packing of the data, because there is a continual debate between the efficiency of packing, as in the bandwidth that's transacted, and the efficiency of the compute operations that need to do all of the data unpacking to allow you to manipulate it. And as we move forward here, I think it's fair to say that the balance is moving towards saying we actually need to be more savvy to the efficiency of the compute than we do to the efficiency of the bandwidth, because of the cost of bandwidth becoming more and more accessible. Almost there, and apologies for my voice, almost running out. I can't believe it's only the end of day one. Our vendor experience. So, as I alluded to, we've relatively recently embarked on instantiating some of the work that's been defined in GCCG, and we've actually found several things that actually need to be embraced there. But what I would encourage everyone that's watching this to do is to actually take a look at the spec that's there. Do give some feedback, because the holy grail we're really searching for is a capability for us to actually have the ability to have interoperability, so the end users in the broadcast space can have efficient compute processes that can work between vendors, so they can have best of breed, choose different software modules to actually implement different elements, and we can have that interoperating efficiently on compute. Hopefully that's been some useful tidbits for what I've said. I would like to invite you for a cup of tea if you're here at the event in the West Hall, which is just only like 1.5 minutes walk from this IP Showcase stand on the West Hall, booth 2130. So do come and see us. Right now, I can tell you, as well as tea, they're also serving beer, if that's of interest. Anyway, so thank you very much for your attention, and thank you for attending any of the other presentations that you've done during this first day of the IP Showcase. Any questions?